So it's an absolute pleasure to be divided here today to speak to you about some perspectives, I think nice European perspectives. And we've already seen a couple great points that we're talking with Luxembourg very strongly on what we can do in Europe to build up this connectivity. And I'm going to talk to you about the things we're doing in Germany to prepare for the perspectives in Europe. And I'm going to be representing here the project QuNET, which is an initiative by the Federal Ministry of Research, Technology and Space in Germany. And it really kind of tries to unite all the components that you need to address the advancement of quantum communication. That is fundamental research by the Max Planck Society's participation, applied research by us, Fraunhofer, participating, and the German Aerospace Center, the DLR, participating to get those prime components that we've already seen in the important satellite missions that we're going to be seeing in Europe. So those are the partners I'm representing. And Rudy already kind of said everything we need to know about the motivation, yeah? Maybe I'll take one more step back and just say the speakers that have been ahead in all the sessions have made it really easy for me to say, if we look at the complexity and the type of resources that are building up in current communication networks, it's very easy to see why we should be thinking about future cybersecurity. Yeah, it's becoming very complex in those networks. And quantum communication is one of the points that the European Union has identified, the Commission, in a emergent technology when we're looking at future developments. And there's enough unity that all 27 member states have signed the declaration to build up a quantum communications infrastructure in Germany. That's a lot of unity. Okay, the declaration is one thing. Hard facts are another thing, and that is exactly what Rudy has presented. In 2026, we'll have the launch date of the Eagle-1 mission, which is the first European demonstrator for a quantum key distribution throughout Europe. And this is why I'm so excited to be here. We're here in the hotspot with SES being the leader and the provider of this mission. And at the same time, we're very proud in Germany that one of the partners in our consortium, there we go. Exactly. One of the four partners whose work that I get to present here today to you, that's Christoph Marquardt, is in the scientific lead for the protocol for this mission, yeah, to make sure that really quantum communication stays quantum communication. So we see this very strong connection that we're trying to build up here. And these are the four people. It's Christoph Marquardt, Fabian Steinleichner, and Florian Moll, and Nino Valenta from Fraunhofer, from the DLR, and from Max Planck, who are driving what I'm going to talk to you about here. And we're also working together with an ecosystem of 26 industry partners, and these are not just a kind of an email ecosystem. This is really funded research and development within this project where the industry is participating in the R&D to the technologies that are relevant for the demonstrations that I'm going to show you. And in the quantum world, we're always really proud when we get that kind of industry participation because it's really difficult, yeah? This is a high invest, very long-term, long-range kind of technology, and getting industry on board exactly to this dimension is kind of a cool thing, so we're very proud of that. In any case, to give you some physics background, you know, when I talked with the organizers here today, I said, so who am I speaking to? Yeah? And they said, well, there'll be some people that definitely understand what you're talking about, and there'll be a lot of people who maybe don't have so much insight into quantum, yeah? And I'm just gonna make it really brief, but pictures are sometimes very powerful, yeah? And I don't have a lot of time to go into this, but whether you're talking about classical communication or quantum communication, light is just an absolutely super phenomenon to encode information on. Yeah, it has so many degrees of freedom, and I've tried to kind of sketch them out for you here, roughly kind of showing what kind of degrees of freedom we're talking about in light. They're actually kind of complex, physical kind of degrees of freedom, but when we have degrees of freedom, that's where we can stick information into, yeah? And I think some of the degrees of freedom we know from the classical world, yeah, for instance, frequency bins, yeah, broadband fiber networks, we know that. That also counts for quantum networks. But now if we look at the kind of technologies that are going forward, what kind of degrees of freedom are we using for quantum communication? Well, all of these are in fundamental research being explored, but if we look at really the first generation technology for quantum key distribution, what are we using? And it's really pretty strongly focused on just these two and this last one here. Yeah? And which means there's a selected pair of kind of techniques that's coming forward, and there's protocols that we're developing to use those degrees of freedoms. And basically the kind of schemes we're looking at here, and I'll be really brief, is that quantum communication allows us to transfer the necessary information to generate what we know already in classic communications is cryptographic keys. Yeah? And the way we do that is, just to give you a feel for this, is we make a so-called superposition of two states of light that are basically laid on top of each other, and the state of light is basically in a hybrid state in both states at the same time. And then if we do this in the way we like to at Fraunhofer, in an entanglement thing, then these states of light that we send to two different communication partners, they remain interdependent even though they're separating in space. Yeah? That's the main part of this. They remain independent even though they're separating in space. And because of the interdependency, for one, the two communication partners, when they measure these signals, yeah, they get corresponding information that allow them to generate a cryptographic keys. And we see we always have two properties that describe these degrees of freedom, and that translates very nicely to the zeros and ones that we know from classical digital world. Yeah. Now, the main part of this is that when we transfer in this superposition state, it's an undefined state. It's not that we're masking a state, and if we could look behind the curtain, we could see what kind of information we're transferring. It's undefined until it's measured. Yeah? That's a law of quantum mechanics, and that's what gives the security principle behind this. Yeah? Now, what we also do is we combine these so-called quantum keys that we extract out of this special kind of transfer that's secure with also keys that we generate with classical algorithms. Yeah? And one could say, why do we do that? Yeah, well, because we are trying to develop quantum communication not as a standalone kind of technology. We wanted to be integrated very deeply into classical security architectures, and so we're trying to pair these together so we can transport quantum into a classical world. Yeah, and once we have that, of course, we do the normal thing that everybody does. We use these keys to encrypt the data that we can send transfer over classical communication channels, and that's roughly how it works. I spend a lot of time on that now. Let's get to some fun stuff. Now, with that picture in mind, and I know it's still a rough kind of cloudy picture, but anyways, just take it. We try to explore what are the best techniques, what are the best kind of methods, what are the states of light that we can best use in different kind of network architectures. Whoops, go back on that. And different kind of network architectures that are going to be elementary in building what we really want to do, a European quantum communications infrastructure. Yeah, that's what we want to do. And I'm not going to describe these individually. I'm just going to walk through the examples that we've been building up in this sense. And the first demonstration that we've had in 2021 was in Germany. They actually let us into the government district, yeah, and they allowed us to go into the government buildings, and we did a link between the Federal Ministry of Research and Technology and Space and the BSI, which is the German National Cybersecurity Agency. And those guys are pretty strict, right? So they're going to watch out what you're going to do in those kind of links and what you're doing in those government buildings. And basically what we demonstrated is we used very many different techniques to see what are the best kind of techniques when we have, first of all, a free space. That means we're going through the mid-air transfer of a quantum state through these two buildings, or if we're using a fiber kind of connection, yeah? And we weighed those different techniques and their security aspects, their practicality, and many other criteria that would be important for a governmental type secure link, yeah? And if you have any questions of that, I can gladly give you some more details after the talk. So the next thing we did, we said, okay, if we're looking at kind of urban scenarios that we want to address and kind of link up different partners that are available in an urban scenario, here in this case, we have the German word down here, Stadtwerke, which are the utility networks, yeah? And we're going to have different partners that are connected in a different way. Some may already have fiber linkage, yeah, into different buildings that are placed here, and some may not be connected at all. And we need to bridge them through free space optical kind of links, yeah? And we also want to build up this network that it works on the very many different kind of protocols and different degrees of freedom that I showed you in the beginning, because as in the real world, we'll maybe have in the future different providers that use different technologies to build up a QKD network, yeah? In any case, this is kind of cumbersome, yeah, when you do this. So you want to learn as much as you can on the way. And one of the big things that's been in question about satellite free space communications, yeah, when you're coming from a LEO orbit down to Earth, is how does this work in daytime and nighttime? Yeah? Because when we're doing quantum communication, we're transferring really single photons, so single light particles, right? And there's all this background from the sun, yeah, that we have to take care of, and we have to isolate single photons that we detect in those special quantum states from all that sunlight in the background. So will this work very well? And we tested it, and we see that here, these light and dark regions are basically the kind of lumens that we have on that day or during the night, just a kind of a gray-white scale. And we see, yes, when it gets really bright, our capability to transfer keys and the rate of those keys get lost in all the noise, yeah, that's in the background. But on the other hand, it's not hopeless. Yeah? We see, if you look at the numbers down here, that the rate in which we can transfer keys is only halved in daytime, nighttime operation on average. Yeah? So this is an important pretest if we want to really get serious about transferring keys from satellite missions, not only in the nighttime and not only when it's not cloudy weather, and only, right? There's a lot of parameters that are bringing up a lot of concerns about how much keys can we transfer when we do satellite QKD, even though it's great that we're getting that outreach across Europe. So the next thing would be, we tested, okay, let's get a little more real even. In Berlin, in the interstate network of Berlin, fiber network, we demonstrated a use case to securing personal data. Yeah? And basically we worked together with the Bundesdruckerei, which in Germany is the institution that's responsible for printing passports and printing security IDs. Yeah? And we built up a scenario of partners together with the German Telecom, which has several locations in Germany, and of course Fraunhofer here, and orchestrating all this, we built up a scenario that looked like this. So we had basically citizens that were logging into a central server, which was played by, I'll say, virtually by the T-Labs, the German, the Telecom Innovation Labs, and orchestrated by so-called a virtual governmental office, which was played by us, where we had secure transfer of citizens of their personal data to basically the issuing service, the Bundesdruckerei, for passports, and then a retransfer of information back, also digital identification documents, back onto the server and taken up by the citizens, right? And of course, this is a lot of virtual in what I was saying, yeah? But what was truly being done was those documents were being printed, yeah? And we showed that we can secure personal data with quantum communication, with quantum key distribution, very similar to the ideas that we're thinking about in Europe on the digital wallet, right? We want a digital wallet that's not supplied just by anybody, but by a secure kind of governmental sort of situation where we can really trust everything, yeah? And these are the steps toward using QKD also in this scenario to making that truly safe for you. So the next one that we're looking at is, we talked a lot about satellite. The satellite's not up yet, but we want to gauge all this. And so we're using these wonderful resources from the DLR in checking a transmission and imaging basically the quantum states we're transferring from this flyer back down to a mobile ground station, and then coupling that into a fiber network, and then basically transferring the quantum state from here all the way to a single atom that's levitated in an electromagnetic trap in this laboratory. And you could say, well, why do we want to do that? Because levitated ions or atoms are the building blocks for quantum information devices in general, just like quantum computers, which we already heard in the beginning in the introduction. And this is already kind of the first step of thinking not only just security, but really quantum information networks, yeah? And taking that step and also seeing how good are we when we transfer quantum states from a high-flying airplane, and this was kind of the trajectory of the airplane. It's about a 10-kilometer radius. This is Oberpfaffenhofen. This is where the DLR has its center. And in any case, these are only first tests that we've been doing. We're actually going to do the demonstration in October. If someone thinks this is really interesting, then watch the internet in October, because we'll have definitely a press release on how well we do on this, yeah? But this is definitely hard pre-work to the Eagle 1 mission. So, yeah, and those are building blocks, and our vision for the future is to say, I've showed you different places in Germany where we do this. Whoops, let me go back. And we've seen Berlin, Jena, Erlangen, Oberpfaffenhofen, and our last push for 2026, when this project will be coming to an end, is to combine everything that you've seen and make a kind of model network architecture, yeah, with all the different components that I've tried to sketch for you really quickly here, to see, can we really build a realistic network out of all these components, or at least demonstrate the key elements of what we need for a quantum network. We're not the only ones doing this, yeah? And if you look at this, basically, in our project, we've been trying to build up sort of on this red line here, kind of a north-south axis within Germany, yeah? So to building up a network backbone. The Deutsche Telekom has kind of been working really hard on this 900 kilometers network or link here between Bonn and Berlin. And there's other projects going on, so we're trying to build up a network in Germany, a realistic network. And why are we doing this? Well, for one, for of course addressing the networks in Germany, but as we heard so nicely from Rudy, we're all excited in Europe because all of us in Europe, just like we are doing in Germany, all other 26 member states are doing the same thing, working really hard on building up their terrestrial networks and getting things moving. And we have a lot of partners that surround us, right? So we try to make our network, so we really reach out to the edges here and try to be very good about trying to make cross-border connectivity, transnational type of connectivity in quantum communication. And that's pretty tough when you think about the regulatory action that's not defined yet for quantum, yeah, and trying to get really nations to come together in their different regulatory actions to build this together. Tough stuff. I'm almost done. Yeah, we're also, of course, Eagle One, we had it. We're also building up ground stations. Let me take a step back. In our consortium, in our set of partners, there's 3 ground stations we're building up. That is the DLR, the German Aerospace. They're going to have one of the reference ground stations for the Eagle One mission. Yeah, they're kind of leading it all to see if this is working. And then we'll have 2 more scientific ground stations. And just to give you an image of what this looks like, this is the one in Jena. This is the one from Fraunhofer. And you see we kind of built our QuDay dome here, the observatory dome. This thing is this telescope that's going to image the quantum states coming down, being signaled down from Eagle One. This is basically finished, and we're almost ready to install it in here. And so we're kind of pre-operational coming up in 2026. Yeah, we're almost set. We're really excited about it. So, as a last point of view, I'd like to say there's an international dimension to this. We also are leading a European project or a set of European partners, which I'll just say are listed down here. That's very impolite of me, but my time is running out. We're working together with Canadian universities and a set of Austrian, Italian, and French research partners. It's a co-funding between the NSERC, which is the National Research Council of Canada funding, as well as the European Union. And I take you back to the picture I showed you in the beginning. We're really, right now, only using just a couple of these states to do this, yeah? And it's all very primitive. It's all just zeros and ones being transferred one by one, very slow. Yeah? We're thinking, are we gonna have enough keys available even to run any kind of system in this slowness? Here is the kind of the project where we're trying to say, okay, let's do this like real classical communication people, yeah? And try to build up and combine different kind of, combine different kind of degrees of freedom that are available to us. This is kind of what this kind of source looks like when you try to do that, and you try to include or multiplex and do high definition quantum state preparation for transferring quantum information. Tough stuff. We're only at the very beginning of this, but we do see this kind of thing exactly in a satellite context, because that's where you're going to fight against very low key rates, because as we learned, we have daylight nighttime problems, we have weather problems, yeah, because we're transferring single photons, yeah, which we can definitely not see, yeah, visibly, very low light levels to all these difficult things. So we want something very robust. So we're trying to combine at least these 3 degrees of freedom, time, polarization, and frequency, and do kind of a multiplexing. And for that, of course, we need to develop these in the context of space-compatible sources. We need to devise fully new protocols, how this works. We need to devise link technologies that are on the ground that can decode what we're encoding in our quantum states. And there's a nice prospect, though, that especially if we're using frequency multiplexing, then we have a nice opportunity of really building up very easily multi-party kind of scenarios. Yeah? Not only just point-to-point kind of things where 2 people are communicating, but really a true network. And I am finished. The only thing I want to say is we develop, build, and produce at Fraunhofer many of these technologies I've shown you here. If any of you are interested in collaborating us into this kind of scene, then here's my invitation to you to contact us. We'd be happy to hear from you. And I'll leave you with the people that made this possible. Thanks for your attention, and I hope I didn't span over the time too bad.
Thank you very much. That was Dr. Torsten Siebert. Thank you, Doctor. Right, yeah, do come in if you want to.